next concept we are going to look at in our Unit C is solution concentration. So solution concentration is a concept that we have to be pretty familiar with throughout the entire unit and knowing how to calculate solution concentration. I'm going to draw your attention to sort of three main types of calculating concentration, and then the last concentration calculation that we do look at is the one that becomes more relevant as we go through both this unit and our following unit on stoichiometry. So let's begin. Concentration is essentially the ratio that compares the quantity of solute to the quantity of solution. So we're looking at how much solute is dissolved in a solvent. Now we have a dilute solution is one where the ratio of solute to solvent is very low. It would be like dissolving 0.5 of a gram into like 10 liters of water, where a concentrated solution would be like dissolving 10 grams into 1 liter of solution. So you might get a difference in concentration depending on how much solute you dissolve in a solvent. Now, in general, the concentration of any solution is represented by this ratio, where concentration is equal to the quantity of your solute over the quantity of your solution. Now, in general, the quantity of your solute will be in grams, and the quantity of your solution should be in some sort of volume measurement. Now, this might be milliliters or liters, depending on the type of concentration that we're going to be calculating for. Now, the first type of concentration that we are going to discuss is called percent concentration. And percent concentration has sort of three main groups of concentrations that we can calculate. The first is a volume over a volume. Another is a mass over a volume. And an additional one is a mass over a mass. Now, scientifically, we use mass over volume, but in terms of what these are commonly known as in terms of our chemicals that we get in the store, so commercial chemicals, this is actually called weight over volume, and this is actually called weight over weight. So this is because of their commercial products, we call them weight over volume. Now, essentially, what we would see is that we need to have some sort of ratio of our solute to our solution multiplied by 100%. So in my example here, let's just say we have 5 milliliters of vinegar and we're dissolving it in 100 milliliters. So this would be a volume and a volume because we have liters and liters. Okay, and what that is saying that if we have 5 divided by 100 times 100%, we get 5% volume to volume. Okay, and this volume to volume is literally just comparing the volume of your solute to the volume of your overall solution or solvent. Okay, so if we take a look at some other examples on how to calculate this, let's just take a look-see. So this is going to be percent concentration using our volume to volume percent concentration. So this says a photographic stop bath contains 140 milliliters of pure acetic acid in 500 milliliters of the bottle of solution. What is the percentage by volume of the concentration of the acetic acid? So when we take a look at this, literally we have our solute divided by our solution. So we get 140 milliliters of our solute divided by the 500 milliliters of our solution. This equals 140 divided by 500, which is 0.28. Then we multiply by 100% to equal 28%. And we would just record this as 28% volume over volume. Now this is just one example of percent concentration. We're going to take a look at another example where we might have to use some different entities. In this percent concentration, we're going to look at a mass over mass, or weight to weight percent concentration. I find percent concentration to be fairly easy because we're dealing with masses, and we're just looking at an overall percentage. So it's a little bit easy. We don't need to think about unit conversions all that much. So this says a sterling silver ring has a mass of 12 grams and contains 11.1 grams of pure silver. What percentage weight by weight, okay, that's weight over weight, concentration of silver is in the metal? So this is when we have 11.1 grams of our silver in our overall ring, which is our total mass, and this equals 0.925. And again, we're going to multiply this by 100%, just like you would calculating your own scores on an exam. And we would say that this equals 92.5% is this pure silver. So this is 92.5% is this pure silver in this overall ring. And we would just call that weight by weight, or weight over weight. Okay. Let's take a look here. So this next concentration calculation, so this is our second type of concentration calculation, is called parts per million concentration, or ppms. You might be familiar with ppms. Okay, this is used for very, very dilute solutions. So when we're dealing with very small amount of solute in our solution. Okay, now in general, if you talk about biology or anything like that, we talk about this in relation to environmental toxins or any sort of toxicological information. So we're talking about maybe how many parts per million of some sort of chemical can be in your body before it causes damage or anything like that. Now, the reason why it's parts per million is often because we're dealing with entities that are either more harmful or that are just very dilute. So we need to talk about it in terms of a small amount for a large volume. So 1 part per million is the same as 1 gram over 10 to the 6 milliliters. Okay, or we can talk about it as 1 milligram per liter. Now, these are the two that we're going to see most often. So a milligram over a liter, or it's equal to a milligram over a kilogram. Now this is a weight to weight parts per million, and this is a weight to volume parts per million, but either you may see them either sort of frequently. So instead of trying to figure out an overall unit conversion, I would suggest converting your solute into milligrams and your solvent into liters or kilograms. Now, liters and kilograms are essentially equivalent units. 1 liter is equivalent to 1 kilogram. One is just a mass measurement and one is a volume measurement, but essentially they are the same thing. So let's take a look at some examples. This says dissolved oxygen in natural waters is an important measure of the health of an ecosystem. In a chemical analysis of 250 milliliters of water at SATP, 2.2 milligrams of oxygen was measured. What is the concentration of oxygen in parts per million? So again, I would make sure that I have milligrams per liter, or let's just do milligrams per liter because we have milligrams and liters. So I want to convert all my units to milligrams per liter or milligrams per kilogram, but in this case we're going to do milligrams per liter. So what it's saying is this: I have 2.2 milligrams in 250 milliliters. Well, 250 milliliters is equivalent of 0.250 of a liter. Because we want our units to be in milligrams per liter, we are going to use this value when we plug it into our equation to figure out our parts per million. This equals, when we divide 2.2 by 250 milliliters, or 0.25 of a liter, we get 8.8 milligrams per liter, or we can call this as 8.8 parts per million. All right, so we can call that 8.8 parts per million. I don't have another example here to look at, but again, just make sure that your units, when you plug them into a parts per million calculation, make sure you don't have a milligrams over a milliliter, because that would be a weight or a weight volume calculation or a percent calculation. We want to see your milligrams per liter or your milligrams per kilogram. That is super duper important. Either one of these two sort of general equations will give you ppms. Now, if we look at our last type of concentration calculations, this is our most common type of concentration calculation, chemistry, and it's called amount concentration. And amount concentration looks at the chemical amount, and if you remember, chemical amount means moles, okay, of solute dissolved in 1 liter of solution. So it's moles per liter. So amount concentration we call C, and C equals your moles, which has always been N over V. So C equals N over V, or amount concentration gives you chemical amount, or moles over volume in liters. So let's just jump right in. We'll look at a few examples here. This says, in a quantitative analysis, in a stoichiometry calculation, produced 0.186 moles of sodium hydroxide in 250 milliliters or 0.25 liters of solution. Calculate the amount concentration of sodium hydroxide. So we take a look at this. I always like to write down what I'm calculating for and what I'm given. So amount concentration is what I'm looking for, my moles, and my volume. So this is a pretty easy calculation. C equals N over V. And I'm just going to plug my numbers in. 0.186 moles per 0.250 liters. When I plug that into my calculator, I solve it to be 0.744 moles per liter. And that is the correct units on that as well. So that was a pretty easy calculation. Let's take a look if we can see or solve for anything a little bit more complicated. Okay, here's another concentration calculation. So this is just, a general concentration calculation. Maybe one where I'm given a concentration and I need to solve for the amount of solute. So this says a box of apple juice has fructose in it, or sugar, and there's a concentration of 12 grams per 100 milliliters, okay, or a 12% weight to volume. What mass of fructose is present in a 175 milliliter glass of orange juice? So if I'm looking at a weight to volume, what it's saying is I have 12 grams per 100 milliliters, and I'm essentially looking for how much is in 175 milliliters. Well, I can essentially cross multiply and divide if I like that, or I can figure out that this is 12% and I need to figure out how much is in 175, so I can divide and then solve for my X value, or what I'm solving for. So what I'm going to do is I'm going to say my mass is equal to 175 milliliters times by my percentage, which is 12 divided by 100, or 0.12. So when I do that, 175 times 0.12, or 12%, equals 21 grams of fructose. Okay, so that's how I would solve for that question. Let's take a look at a different example. This says a sample of well water contains 0.24 parts per million of iron sulfate dissolved from the surrounding rocks. What mass of iron sulfate is present in 1.2 liters of water in a kettle? So again, I'm given my parts per million and I need to calculate for a mass. So I can either say, remember that parts per million is milligrams per liter, and this equals, I'm asking for 1.2 liters, and I'm looking for this guy, so again I can cross multiply and divide. Or I can say I have 1.2 liters, and I'm going to multiply by my 0.24 milligrams per liter. And when I do that, my units will cancel out like so. And I will get, again, this is the same thing as cross multiplying and divide, I will get that I have 0.29 milligrams of, because my unit is milligrams, of iron sulfate in my kettle. All right, so these are sort of simple calculations. Generally, they're involving a cross multiply and divide. Here I would, again, I cross multiplied 0.24 times 1.2 divided by 1, and I get my answer. Another example, this says a sample of laboratory ammonia has an amount concentration of 14.8 moles per liter. What chemical amount of ammonia is present, so our chemical amount, remember, is moles, is present in a 2.5 liter bottle? So if I rearrange my formula, I initially have C equals N over V, but if I rearrange my formula to solve for N, or moles, I'm going to multiply by my volume, and I'm going to multiply by my volume on the other side, so I get N equals C times V. So when I go to plug these values in, I get my concentration of 14.8 moles per liter times by my volume of 2.5 liters, giving me an answer of 37 moles in my 2.5 liters. So 37 moles is my correct answer here. So again, I'm only using 3 variables. I do need to rearrange my formula initially to solve for my chemical amount. If we take another look at another question here, this says a chemical analysis requires 2 liters of 0.150 moles per liter of silver nitrate. What mass of silver nitrate is needed to prepare this solution? So in this question, I'm given my volume. My volume equals 2.0 liters. My concentration equals 0.150 moles per liter. And my mass is what I'm looking for. Now, because I have only my formula C equals N over V, I probably need to somehow solve for my moles. Now, once I solve for my moles, I can potentially use an additional formula to solve for my mass. So let's begin by solving for my moles. So again, from our previous slide there, we know that N equals C times V. So my concentration of 0.150 times by 2 liters, this gives me, I don't need a bracket there, this gives me 0.30 moles per liter, or just moles, pardon me. 0.30 moles. Not moles per liter, just moles. So then I can potentially say, okay, well my mass, I know this from my other units here, but my mass is equal to my moles times by my molar mass. Well, when I take a look at silver nitrate, there's a good potential that I can calculate for my molar mass. So my molar mass of silver nitrate is equal to, well, nitrogen, I have 1 times nitrogen, which is equal to 14.01, 3 times my oxygen, which is equal to 36.00, and my silver, I'm going to need to look at my silver. I don't remember that value off the top of my head. My silver is equal to 107.87 grams per mole. So when I solve for my total molar mass here, I get 0.88. 9 and it went 169.88 grams per mole. So when I go to plug these numbers in, I simply plug in the number of moles, which is 0.30 moles, times by my molar mass, which is 169.88 grams per mole. And when I plug that into my calculator, I get that this equals 51.0 grams. So in order to create a 0.15 mole per liter solution of silver nitrate, I'm going to need 51 grams of silver nitrate to weigh out, to measure that amount to dissolve into my 2 liters. Another example here, this says a student dissolves 5 grams of solid sodium carbonate to make a 250 milliliter solution. What is the amount concentration? So let's write these variables down. I'm given mass. Mass equals 5.0 grams. I'm given that it's sodium carbonate, but I'm also given my volume. And I'm going to convert this to liters because I'm pretty sure I'm going to have to use my liters as my units, and I'm looking for my amount concentration. Well, similarly, I maybe need to use a different formula first to solve for my moles, because I know my concentration formula is equal to C equals N over V. So initially I need to solve for my number of moles. Now, sodium carbonate is Na. Let me just see here. Okay, Na2CO3. So we have sodium carbonate, Na2CO3, and our molar mass for this, I'm just going to give you the molar mass because I'll do the calculation. And I'm just, at this point, if you don't know how to calculate molar mass, you probably need to go back and figure that out. So I'm going to give you the molar mass in this case, just in the essence of saving a little bit of time, but please, 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 please do ensure you know how to calculate molar mass. So it's 105.99 grams per mole. Okay, so when I plug in my calculation to calculate for moles, I know that my moles is equal to my mass over my molar mass. So I have 5 grams divided by my molar mass, which is 105.99 grams per mole. This gives me a value of 0.472 moles. Now, once I've solved for my moles, well, I look back at my formula here, my calculation that I need to do, and I can plug in now my moles and my volume. So I have 0.472 moles divided by my volume of 0.250 liters. So this gives me an answer of 0.189 moles per liter. All right, so you can see how if I'm given mass, I can solve for moles and then plug that into my second formula here, or vice versa. If I'm given a concentration and a volume, then I can backwards do my math and solve for mass. So mass and chemical amount are often tied together quite closely. So a couple more things that we need to talk about before moving on is that we can also look at the concentration of particular ions. So when we have ionic compounds or strong acids in solution, if it's an ionic compound or a base, they dissociate. If it's an acid, they ionize. So for example, if I have NaCl, we've seen this example before, it dissociates into Na positive and Cl minus. Or inversely, if I have another example, calcium chloride, CaCl2, gives me calcium 2 positive and 2 Cl minus. Again, I have to have 2 chlorines because I can't lose atoms. Another thing to notice is that I have a 2 positive charge and 2 times a negative charge, with 2 negatives and 2 positive cancels out to be a neutral charge, which on both sides of my equation I also have a neutral charge. So that's pretty important to remember as we go through. Now this question says, what is the amount concentration of aluminum ions and sulfate ions in a 0.4 mole per liter solution of aluminum sulfate? So let's just start by drawing out our dissociation equation. I know that it's the dissociation because it is an ionic compound. So aluminum sulfate dissociates into aluminum, and I have 2 aluminums, and they're aluminum ions, so they have a 3 positive charge. And I have 3 sulfates with a 2 negative charge. Again, I need to make sure that my charges balance out and cancel out, so I have 2 times 3 positive and 3 times 2 negative, which are canceled out to 0. So if I'm looking for my concentration of my aluminum ions, well, I know that and concentration is determined, and I can put square brackets. What's going on here? Square brackets. That just means concentration. So concentration is equal to square brackets. So if you ever have square brackets around any sort of entity, like I have it here, it's my concentration of aluminum ions. Now, essentially, I have a concentration of 0.4 moles per liter of this entire entity here. Okay, this is equal to 0.4 moles per liter, but I want to look at what happens when this compound dissociates. So I have 0.4 moles per liter, but that was just of my original solution. Well, when this dissociates, I have twice as many aluminum ions as I do my original compound. I only have 1 mole of aluminum sulfate, but 2 moles of aluminum ions. So I have, again, this thing that you might remember from your gas laws, but it's kind of like using this mole ratio. I have 1 mole per liter of aluminum sulfate, and I have 2 moles of aluminum ions. So it's a 2/1 mole ratio, which you might remember, which is equal to a concentration of 0.80 moles per liter. So I have a greater concentration of my aluminum ions individually than I do of my entire entity. Now again, this is just because this breaks down into 2 Al3 positive and 3 sulfates. Again, I didn't really gain any concentration. It just has more aluminum ions than there is of this complete compound. Now, if I'm calculating my SO4 2- concentration, again, square brackets mean concentration, I still have 0.40 moles per liter. And if I look at my entire entity of aluminum sulfate and my sulfate individually, I have a 3/1 mole ratio, which means that I have, and again this would cancel out, I would have 1.20 moles per liter of my sulfate ions. So if I need to calculate the concentration of one of my ions, I have to look at the dissociation, the balanced dissociation equation or ionization equation, to then get a value of my mole ratio to plug those values into to solve for my individual concentrations. Now please don't be confused. It's not saying that I can add 0.8 and 1.2 to solve for my overall concentration. That's not exactly how it works. If you think of it as a marker pen that has a lid and just the marker itself, what's happening is if you have a marker and you take the lid off from that marker, you have a lid and a marker, which is kind of what we're doing here. We have your entire marker and then you break it up into the lid and its marker. Now what this is saying, that it's not a typical marker in this example. Essentially, in this question, you have a marker pen that has 2 lids, but 3 sort of bases, 3 main portions of its marker. So when you break it up, you just have 2 lids and 3 marker pens. So you just have twice as many lids as you did your original marker pen, and then you have 3 times as many bases once it's broken up as your original. So please don't get confused that you can't just simply do regular math where you go 0.8 plus 1.2 gives you your total solution concentration. That isn't quite how it works. You're actually breaking a compound down. All right, let's just take a look at one more example here. What mass of magnesium bromide must be dissolved to make 1.5 liters solution with a concentration of 0.3 moles per liter? So again, let's start out with magnesium bromide, MgBr2, dissociates into Mg2 positive and Br minus, but I have to have 2 of those guys, so don't forget that. Now, my original concentration of magnesium bromide is going to equal, my total concentration of magnesium bromide is my 0.30 moles per liter. Now remember, this is moles per liter of bromide ions, so this is Br minus. Again, I'm going to multiply it by my mole ratio. Again, my mole ratio is really important. I, again, like to prefer to do a unit cancellation rather than doing the required over given, but if you prefer your required over given ratio, then that is fine. And my mole ratio is for 2 bromines, I have 1 magnesium bromide. So I'm going to multiply by 1, divide by 2, or just multiply by 1/2. And this is going to equal out to be 0.15 moles per liter. So once I've calculated my overall solution concentration of magnesium bromide, I then can see my moles. So my moles is equal to concentration times volume, which all I've done is rearrange C equals N over V to get this formula here. And my moles is equal to my concentration times my volume. Because I'm looking for mass, I know I need to solve for chemical amount. So that's why I'm solving for N here. So when I go to plug in my values here, I get 0.15 moles per liter times by my volume, which is equal to 1.50 liters. This gives me a molar amount of 0.23 moles. So once I've solved for my moles, I can now solve for my mass. Let's do this in pink. My mass is equal to my moles times my molar mass. And again, I'm going to give you your molar mass of magnesium bromide. I need to add up my magnesium and 2 bromides, and my molar mass is equal to 184.11 grams per mole. Again, I'm giving you that just in the essence of saving some time. So this equals my moles, which is 0.23 moles, times by my molar mass, which is equal to 184.11 grams per mole. And when I simplify and solve that, plug those values into my calculator, I get that this is equal to 41 grams. Okay, so basically I had to go through what I know about dissociation. I had to go through my mole ratio. Remember, I do this as unit cancellation. I cancel out bromine is equal to bromine over 1, or required over given. I'm looking for magnesium bromide, which is required. I'm given a value for bromine or bromide ions, so that's my given. So it's 1 over 2. I get my concentration of magnesium bromide. Again, my square brackets represent concentration. Once I get my concentration, I can calculate my number of moles. I calculated my moles to be 0.23 moles. In order to calculate mass, I know that mass equals moles times molar mass. This is a calculation I've done several times at this point because I've done it since Science 10. I get 0.23 times my molar mass of 184.11. Probably had to do a calculation here to solve for my molar mass, getting me my answer of 41 grams. So you have a variety of ways that you can calculate concentration, starting with percent concentration, parts per million concentration, and amount concentration. And as you've seen, our amount concentration tends to be what we use consistently in our chemistry units, as well as in the lab. Primarily is our amount concentration. So make sure that you're on top of this amount concentration. If you need to go through some practice questions, you can take a look either online or in the textbook to do some practice questions prior to going into your assignment. So good luck!